Welcome to this comprehensive training on context engineering for large language models. I'm excited to guide you through this revolutionary approach that's transforming how we build and deploy AI systems in production environments. Context engineering represents a fundamental shift from traditional prompt engineering to a more sophisticated, systematic approach for managing the complete information payload provided to large language models. Unlike simple prompt crafting, context engineering encompasses the orchestration of instructions, knowledge, tools, memory, state, and user queries into a cohesive, optimized context. Let's begin by understanding the evolution of LLM interaction. In the early days of large language models from 2018 to 2020, we relied on simple prompt response paradigms with minimal context awareness. This evolved into the prompt engineering era from 2020 to 2022, where we focused on crafting static prompts to guide model behavior. The introduction of RAG systems from 2022 to 2023 marked a significant advancement by augmenting prompts with retrieved information from external sources. Today, we're in the context engineering era, which takes a holistic approach to managing the complete information payload. The limitations of static prompting have become increasingly apparent. Traditional approaches struggle with complex multi-step tasks, have limited access to large-scale external information, cannot adapt to changing information needs, and lack the scalability and reliability required for enterprise applications. This paradigm shift moves us from tactical prompt crafting to strategic context orchestration for enterprise-grade AI systems. Now, let's explore the mathematical framework that underlies context engineering. While traditional prompt engineering treats context as a simple string where context equals prompt, context engineering decomposes context into multiple structured components. The context assembly function orchestrates instructions or system prompts, knowledge from retrieved relevant information, tools or available function definitions, memory including conversation history and learned facts, state representing the current world or user state, and the user's immediate query. This leads us to the optimization problem at the heart of context engineering. We seek to find the optimal assembly function that maximizes the expected reward of the LLM's output given the target, subject to constraints including context window limitations, knowledge retrieval from databases, memory selection from history, and state extraction from the world. The Bayesian framework provides a theoretical foundation where the optimal context is inferred based on the probability of context given query, history, and world state. This formulation enables uncertainty quantification, adaptive retrieval, and multi-step reasoning across interactions. When we compare prompt engineering to context engineering, the differences are striking. Prompt engineering lacks a formalized mathematical model, has unclear optimization targets, is limited to prompt text complexity, uses fixed information content, has no state functions, scales linearly, and relies on manual prompt inspection for error analysis. In contrast, context engineering employs a Bayesian framework, uses multi-objective optimization, handles the full information payload, enables adaptive information maximization, includes explicit state tracking, supports parallel processing with compression and filtering, and provides systematic component evaluation. Performance comparisons show context engineering significantly outperforms prompt engineering across all capability areas, including complex tasks, external knowledge integration, memory management, tool integration, and enterprise-scale applications. The core components and techniques of context engineering include several key building blocks. Context scaling involves position interpolation, memory-efficient attention mechanisms, and techniques for handling ultra-long sequences of 100,000 tokens or more. Structured data integration incorporates knowledge graphs, graph neural networks, and structured data processing for enhanced context representation. Self-generated context enables autonomous reasoning, iterative refinement, and self-improvement mechanisms for context evolution. Memory systems provide persistent context, hierarchical memory structures, and long-term storage for maintaining context across interactions. Retrieval-augmented generation, or RAG, serves as a crucial component in the context engineering framework. RAG combines retrieval mechanisms with generative models to enhance responses with external knowledge without retraining the model. The RAG process flow begins with query processing, where user queries are analyzed and transformed into search queries. Next, relevant documents or chunks are fetched from knowledge sources during the retrieval phase. The ranking and filtering stage ensures retrieved content is ranked by relevance and filtered appropriately. Context assembly then formats and assembles selected content into context. Finally, the LLM generates responses based on the query and assembled context. Advanced RAG techniques include hybrid search combining semantic and keyword search, multi-step RAG with iterative retrieval and reasoning, and self-RAG with self-reflective retrieval decisions. In the context engineering framework, RAG serves as the knowledge component in the context assembly function, where knowledge equals the retrieve function applied to the query and database. Implementation architecture requires careful system-level design considerations. The retrieval layer is responsible for fetching relevant information from knowledge sources, including vector databases for semantic search and hybrid retrieval strategies. The orchestration layer manages context assembly and component integration through dynamic context composition and token budget management. The reasoning layer provides core LLM processing with context-aware capabilities, including multi-step reasoning and self-reflection. The memory layer maintains state and conversation history through short-term working memory and long-term persistent storage. Implementation challenges include token limitations requiring careful management of context within model constraints, relevance optimization to ensure retrieved information pertains to the query, component integration for seamless coordination of multiple context sources, and latency management to maintain performance with complex context. Real-world applications demonstrate the practical value of context engineering. Enterprise applications include conversational AI assistants that maintain context across complex multi-turn conversations, intelligent document processing systems that understand and reason about information across multiple documents, AI-assisted development tools that understand project context and coding standards, and business intelligence systems that combine natural language queries with contextual understanding of business metrics. Case studies show remarkable results. A scientific research assistant reduced literature review time by 70% and identified cross-disciplinary connections that researchers had missed. A customer support platform achieved 40% faster resolution times and 35% improvement in customer satisfaction scores by integrating product documentation, customer interaction history, and real-time system status. Looking toward the future, current limitations include context window constraints despite advances in long context models, retrieval quality challenges with nuanced understanding of query intent, computational overhead that can introduce latency, and the lack of standardized evaluation metrics for measuring context quality. Research opportunities abound in areas such as context compression, multimodal integration, retrieval optimization, memory systems, evaluation frameworks, and self-evolving systems. Emerging paradigms include multimodal context integration incorporating visual, audio, and other sensory data, adaptive context compression with dynamic techniques to prioritize context elements, and self-evolving context systems that learn and adapt their assembly strategies through continuous feedback loops. In conclusion, context engineering represents the natural evolution from static prompting to dynamic, context-aware AI systems capable of handling complex enterprise requirements. Successful implementation requires a systematic approach to context assembly, component integration, and optimization across multiple dimensions. Organizations implementing context engineering see significant improvements in AI system performance, reliability, and user satisfaction. Key implementation steps include assessing current AI system limitations and context requirements, designing context assembly architecture with clear component boundaries, implementing retrieval mechanisms optimized for your knowledge domain, and establishing evaluation metrics to measure context quality and impact. Resources for further learning include research papers such as A Survey of Context Engineering for Large Language Models and The Prompt Report, a systematic survey of prompt engineering techniques, as well as open source tools like the Awesome Context Engineering Repository, LangChain Framework, and Llama Index Data Framework. The future of AI interaction lies in sophisticated context management. As we move forward, context engineering will become the standard approach for building production-grade AI systems that can truly understand, reason, and adapt to complex real-world requirements. Thank you for joining this comprehensive training on context engineering. I encourage you to explore these concepts further and begin implementing them in your own AI projects.